Well, when we think about mixing solids with liquids or liquids with liquids or gases with liquids, what we have to ask ourselves is there some sort of physicalness to this? Is there something I've seen that suggests that this mixing occurs? And in fact, there is. You guys see this all the time when you're mixing things together. One obvious example involving solids is when you dump sugar into water or salt into water. And when you talk about the fact that mixing has occurred, the way you know that mixing has occurred is if you see some sort of homogeneous solution that results from it, as opposed to it remaining heterogeneous, remaining in some way unmixed. So here is a powder being added to a liquid. This is, for example, potassium chlorate. It's a salt. As it sits here and it gets dumped in there, initially what you see is an intermediate non-equilibrium result as we wait for the mixing to occur. But given time, we get to the point where, in fact, I have a homogeneous solution here. And I would say at that point that the potassium chlorate here has, in fact, dissolved in the liquid. And because it is soluble in the liquid, I refer to this as a solution which is mixed, is at equilibrium. Delta G is equal to 0. So the question we're going to ask is, what things do that? When you dump a solid into a liquid, what things dissolve and end up looking like this, and what things do not? When I think about what delta G is like in the process, it's the same kind of argument you can imagine that we've seen with other things, that if the mixing happens, then delta G is negative. If the mixing doesn't happen, so if I retain that heterogeneous result, then delta G is positive. We can make the same kinds of arguments about what happens when you mix liquids together. And you were certainly familiar with this. Imagine what happens when you take water and you mix it with ethanol, as opposed to when you take water and you mix it with oil. Right here is an example of oil and water being put together. Notice that they end up creating these two separate layers here. And they make these two separate layers because they do not mix. They are known as immiscible. Delta G is positive with respect to this mixing process. On the other hand, there are solutions that you can mix together. I gave you one example, water and ethanol, where what you see afterwards is a nice homogeneous mixing occurring. You would say then that delta G is positive in this case, and you have an immiscible result. And delta G is negative. The delta G of mixing here is negative. You have a miscible, a homogeneous solution that results from it. And the question we'll ask is, why do some things do this, and why do some things do this? When we talk about the mixing of gases into liquids, it's actually a little bit more boring than that, because most of the gases that mix with water, for example, do so in such a way where after it's done, it doesn't appear to be any different than before, because we don't have any obvious ability to observe oxygen or nitrogen or helium as it bounces around in the atmosphere. But in fact, it turns out that you can dissolve oxygen, nitrogen, and helium in water. Just ask a fish about oxygen being dissolved in water, and it will tell you that there's some there. And there's actually a thermodynamic argument that can be made for why it is that these small molecules, in fact, are able to dissolve and achieve some sort of solubility in water. So we're going to explore that particular case as well.